please hit subscribe.
Continuing with our tips and tricks for verifying divergence and convergence, let us look at the ratios of successive terms in a sequence and see how they can help us determine the divergence or convergence of a sequence. We will begin with the intuition that two successive terms in a sequence, a sub n plus 1 and a sub n, approach the same number, the limit L, as n becomes very big. In the previous video, we looked at the difference of these terms, and we intuited that the difference gets closer and closer to 0 as n approaches infinity, because the limits of the terms, these two terms, approach the same number, and so their difference must also approach 0. Here, we will look at their ratio. What will happen to their ratio if they approach the same limit? And the first statement is rather obvious. We say that if the sequence converges to a non-zero number, so suppose we already know that they have a limit, then the limit of the ratio is equal to 1. And again, we have a condition here that says non-zero. The reason that it's non-zero is because if it were 0, then we are dividing something that is approaching 0 and something that by something that is also approaching 0, and that's a form that is called indeterminate because we cannot extract information. It could be something very big, very small, or something that is a constant. So we don't really have information when it's 0 divided by 0. And so here we will constrain ourselves to non-zero limits. Now, we will show that this is true. It's obvious, but we will show that it is true so that we will be confident with the succeeding conclusions. So here's the proof. The sequence a sub n converges to the limit L, which we say is not equal to 0, if and only if that L is equal to this limit and this limit. So that's what we mean by something that converges to L. It will have a limit L. So a sub n will have a limit L. A sub n plus 1 will also have a limit L. That's what it means to converge to L, right? And now let's compute this ratio. Now, because we know that a sub n does not converge to 0, we can separate the limits into a numerator and a denominator. If a sub n were approaching 0, we cannot do this part here. But because we know that it's not approaching 0, we can do this. We can separate the limits. Now the limit in the numerator is L, and in the denominator it's also L, and so it's equal to 1. And so this statement is true. Now let's show an example of what we mean by this statement. So for example, we know that this sequence converges to E, and therefore if we take the limit of the n plus first term, of the ratio of the n plus first term to the nth term, so the numerator here is the n plus first term, or a sub n plus 1, so that becomes like this, and the denominator is just a sub n, and so this is the denominator. And what this statement says is that the limit of this whole expression here must be 1. And we know that that is true because we can actually do the following. We can take the limit of the numerator and then take the limit of the denominator, because we know that it converges to E. So we first have to know that it converges to E. And then when we do that, the numerator here, it's n approaches infinity. If we change that to n plus 1 approaches infinity, now here, here, and here are all the same variables, and so it has the same form as the denominator, and so this numerator also approaches E, and the denominator also approaches E, and therefore E over E equals 1. And so we have we have a conclusion that is very consistent, or rather consistent with this statement. Now, we will look at the counterpositive, or rather the contrapositive of this statement. And we know that the contrapositive will have to be equivalent, logically equivalent to this statement. And so the contrapositive is just another way of stating the same statement. The contrapositive, if we recall, is the negation of the conclusion here, implying the negation of the hypothesis here. So the negation of this conclusion part is that the ratio is not equal to 1. The limit of the ratio is not equal to 1. You see that? And the negation of the hypothesis here is that because it says the sequence converges to a non-zero number, the negation of that is that the sequence either diverges or it converges to 0. So these two statements are equivalent. And now we can see that this is gonna be a useful way of testing for divergence or convergence, because if we can get this limit and it's not equal to 1, then we can say whether the sequence diverges or converges to 0. Not only converges, but converges to 0. That's a stronger statement. So what we'll do is we will break this into two cases. Not equal to 1 means either the value is less than 1, in which case it converges to 0, or the value is greater than 1. That means it diverges to 0. We will prove that if it's less than 1, then it converges to 0, and if it's greater than 1 here, it actually diverges. We will prove these two at the end of this presentation. But before that, let's look at some examples. And even before the examples, let's just emphasize that if the value is equal to 1, then we have no idea, because this contrapositive is not saying anything when it's equal to 1. It just says something when it's not equal to 1. So if it's equal to 1, no idea, we cannot use this test. Now let's go to the examples. So the first example is, does this sequence a to the n over n to the k, where k is greater than 0, does it converge to 0 or does it diverge? So we'd have done this in a previous video. You can see the link here, you can click that for the previous video, and we just used the binomial expansion for that. But here we will just use this test that we have developed. So let's just write down this limit. So this limit here, the numerator is just the n to the first n plus first term, and that's just a to the n plus 1 over n plus 1 raised to the k, and the denominator is just as is, a to the n all over n to the k. Now this is rather easy, so a to the n plus 1 over a to the n, it simplifies to a, and then this denominator here divided by this denominator here simplifies to this term here. And then if we just factor out the a from the limit, because a is just a constant, then we are left with this limit here, and interestingly we already know that this limit actually approaches 1, right? Because you have here the n, and this term here approaches 0. This is just a constant here, so it won't matter. And so we have something that approaches 1, and so this whole limit is equal to a. And we are asked whether it converges or diverges. So let's look at the test. The test says that if this limit, in this case this limit is equal to a, if this limit is less than 1, then it converges to 0. If this limit is greater than 1, then it diverges. And so we are now left to conclude that a determines whether the limit actually diverges or converges. In fact, because this is the limit, here, and this is the value, we can see that if a is less than 1, meaning this limit is less than 1, we have a sequence that converges to 0. And if a is greater than 1, meaning this limit here is greater than 1, we have a sequence that diverges. And this is a much faster way than using the binomial expansion like we did in the previous videos we have. Now let's look at another example. Again, this example has been solved in a previous video. You can look at the video using this link here. And again, we are asked to tell whether it converges or diverges. Let's just write the limit of the ratio. Again, this is not a very difficult task. You just write the n plus first term and the nth term. We do some algebra. It becomes like this. And again, this is an easy limit to evaluate. We just get a again. And this is the same limit as what we had in the previous slide. And so the convergence is also the same as the previous slide. If a is less than 1, it converges to 0. And if a is greater than 1, this sequence diverges. Again, we see that a determines whether this sequence diverges or converges. And again, if a is equal to 1, we cannot say anything, but clearly we can say from looking at the given that if a equals 1, then this actually diverges, because we'll be left with n times 1 here. Okay, but we cannot use this test to say that. We have to look at the whole given. The next example is again from a previous video where we used the binomial expansion to compute the limit. Again, it's not a hard task to actually just substitute the n plus first term, then the nth term, and again we get a simple looking limit, and the limit is again a. And again, that means that if a is less than 1, we get convergence to 0, and if a is greater than 1, we get divergence. And again, we cannot use this test if a equals 1. If a equals 1, we cannot use this test, but we can see that it will become n squared times 1, and so we know it still diverges when n equals 1. Now we're down to our last example, a to the n all over n factorial. So does this converge to 0 or does it diverge? Again, we just write the ratio first, and we substitute the n to the n plus first term and the nth term. This is what we get, and we see that a raised to the n plus 1 and a raised to the n cancels. We are left with a, and in the denominator and the numerator n factorial cancels. We are left with n plus 1. Now n approaches infinity. As n approaches infinity, this limit goes to 0, and because 0 is less than 1, we fall in this case, and therefore this limit actually converges to 0. I have promised to show a proof of the tests that we've developed in this video. However, in the interest of time, let's move that to the next video. Let us just state the conclusions from this video. Again, the test that we have developed here is based on the intuition that two successive terms in the sequence, the limit of these terms as n approaches infinity is actually the same limit L. And so in the previous video, we showed that, or rather we used that by actually saying that the difference between these two will approach 0 because they're getting closer and closer to each other. So they would approach 0. The difference would approach 0. Now here, instead of using difference, we use the ratio. Again, because we're approaching the same limit, we say that if the sequence converges to the limit L, and let's put the restriction that it's not equal to 0, the limit is not equal to 0, then what we can say is that the limit of their ratio approaches 1. Again, the intuition is that because a sub n plus 1 and a sub n gets closer and closer to each other. Now, we take the contrapositive of that to actually get the test that we want. So the contrapositive is that if this limit here is not equal to 1, and not equal to 1 means we have a case where it's less than 1, and we have a case where it's greater than 1, then the sequence either converges or diverges. And in fact, we can show, which we will do in the next video, that if this limit is less than 1, then a sub n converges to 0. Not only does it converge, but it converges to 0. So this is a stronger statement than just saying that it converges. And we also will show that if this limit here is greater than 1, then the sequence diverges. We used these tests, these two tests, to actually recompute the limits. Here, we have computed these limits previously using the binomial expansion of constants here, but in this video, we used these two tests to actually compute the limits more easily, and we also computed this new limit here. So in the next video, we will show the proof for this test, and we will also extend this test to series, which are just special sequences where the terms are sums of another sequence.